Hello, I'm Jonathan Aldrich. Let's put on our architecture hats again and talk about instruction set architecture and how architecture affects the implementation of programming languages. Instruction set architecture refers to the set of instructions available on a machine and how they are encoded into bit patterns. The different kinds of instructions include computational instructions, which would include arithmetic operations like plus, logical operations like and, tests, and comparisons. Data movement operations allow us to move data between registers or between registers and memory. Finally, control flow operations allow us to branch from one instruction to another, either an unconditional branch where we just go to the target instruction, or a conditional branch where we go to the instruction dependent on some condition. Control flow operations also include calls and traps to the operating system. The encodings of instructions can be fixed. For example, all instructions fit in one 32-bit word, or they can be variable length. Making them fixed makes the processor implementation simpler, but variable length adds flexibility in the architecture. Some processors allow compressed 16-bit instructions, which helps make code shorter at the cost of some flexibility in the instruction set that's available for those 16-bit instructions. There are two families of design. One is reduced instruction set computing. Those machines have fewer and simpler instructions than complex instruction set computing machines. In general, the world of architecture has been moving over the past 30 years more towards the reduced instruction set computing machines. Some of that happened because of some of our programming language people. So John Hennessy and David Patterson, along with John Cook at IBM, pioneered the design of reduced instruction set computers. Hennessy and Patterson are known for their work in computer architecture, where they wrote an excellent textbook. And if you want more information about computer architecture than is in our book, their book is a good example of that. But they've also made important contributions to programming languages and implementation techniques. They shared the Turing Award in 2017. John Cook also got the Turing Award, I believe, in 1987. John Hennessy is currently the chairman of Alphabet, which you may know as the parent company of Google, was previously the president of Stanford University, whereas David Patterson is a professor at the University of California, Berkeley, and served as the president of the Association for Computing Machinery, the main professional organization for computer scientists, from 2004 to 2006. Let's talk about addressing mode of machines. In RISC machines, computational instructions only operate on registers, so data must be loaded into registers before use. Complex instruction set machines, or CISC machines, often allow memory access for one operand, whereas the other operand has to be in a register. Binary instructions, such as add, may have either 2 or 3 addresses associated with them. If we have 2 instructions, then our instructions are shorter, whereas 3 instructions make code generation more flexible. If there's only 2 instructions, then one of the instructions is also the destination. So we say, register A should be assigned the value of register A plus register B. Addressing modes are used to access the memory. So an addressing mode may include features like a displacement, which is a base register plus a fixed offset, or an indexed addressing mode. So an indexed addressing mode will add the values of a base register and an indexed register. This is good for array-based computations, right? So the base register would hold where the array exists, and then an index register would show how far into the array we have to go. In contrast, displacement might be very good for accessing data on a stack. So we take the base register, which might be the frame pointer, and add a fixed offset to it to get to a particular variable. The x86 supports a somewhat more complicated mode. It allows us to take one register times some small constant C1 plus some other register plus some constant C2. So this might be useful if we have, if register 2 is our frame pointer, and then C2 is the address of an array, and then we're indexing into that array with register 1, but the array is holding words, not bytes. And so we can access location 3 if register 1 has 3, if C1 is the word size, perhaps 4 bytes. On many architectures, we branch conditionally based on condition codes. These are bits in the processor status register that are set by most instructions. we'll set those bits if the instruction produces a value that's 0 or a value that's negative, or if there was some overflow in the computation in that instruction, or if there was a carry bit set. So for example, let's look at how we might implement a condition code, an if statement that's based on a computation. So let's assign a to b plus c, and then if a is 0, we'll branch to some body. On the x86, we could write that code as follows. This is in GNU assembler notation, so the destination comes last. If you've used Microsoft or Intel compilers that have put the destination first, just reverse that in your head. So on the x86, we will first load C into a register, move C into EAX. Then we'll add B to EAX, right? So remember, x86 has a register mode. It's a complex instruction set computing system where add can take a memory operand. So we'll load from B in memory to EAX and add it with C. We'll store EAX back into A. And then we'll jump if the result was not equal to 0. So JNE is jump if not equal to 0, we'll jump to N1. And then if it's equal to 0, we just fall through and we execute the body. So what does result not equal to 0 mean? That just means the latest result that computed something. A move doesn't compute anything, and so our condition flags will have been set by the add instruction. Another thing that can be used for conditionals is a conditional move. So sometimes a conditional move instruction makes code shorter than if we tried to implement the same thing with conditional branches. So for example, what if we want to compute the maximum value of A and B and store it into C? Well, we could move B into ECX, move A into EDX. We can then compare ECX and EDX. That tells us which one is larger. And then if A, which is stored in EDX, is greater than C, then we'll move it into ECX. And then ECX will be the value, the resulting value. We'll go ahead and store that in C. Some architectures allow almost any instruction to be made conditional. This is called a technique called predication. Let's talk about how modern architectures are implemented and how that affects compilation. So pipelining is a technique that's used to make the processor operate more efficiently. Modern architectures are able to overlap the execution of multiple instructions. The way they do that is that instructions are executed as a sequence of different sub-operations. So first we have to fetch the instruction from memory. Then we have to decode it. That tells us, that looks at the bits and determines, what instruction we're trying to do. Are we trying to do an add or a subtract or a jump? We then fetch the operands from the registers. So we get, if we're doing an add, we get the two numbers we're going to add from the registers into the addition unit. Then we do arithmetic computation. So that will be done in the arithmetic unit, or ALU, arithmetic and logic unit, it's often called. Then there might be a memory access. So if we are accessing memory as part of our instruction, we're doing a load. This would be the point at which we get the data from the load, and finally we write back to the register. What pipelining does is it allows the different stages of instruction execution to overlap with the execution of different instructions. So our first instruction will do a fetch, and then when we do a decode for that first instruction, the next instruction can be fetched. And then we can move on down the pipeline. So at the point where the first instruction is writing back to a register, the second instruction is doing its memory access, the third instruction is doing arithmetic computation. For the fourth instruction, we're fetching operands, we're decoding the fifth instruction, and the sixth instruction is just getting started with an instruction fetch. What this does is it allows us to keep the multiple functional units, the units that are doing all of these different operations, busy at the same time. So we're making efficient use of the hardware, and we'll be able to complete more instructions per second because we're doing all of different parts of the work for different instructions all in parallel. So even if one instruction takes 6 cycles to execute, we can overlap that with 5 other instructions, and so we can get one instruction done every cycle. That's the optimal case when we can just pipeline one instruction after another. In practice, pipelines might stall, and these stalls reduce efficiency. So for example, if two executing instructions need the same functional unit at the same time, that would cause a stall. If a result computed by one instruction is needed by another, but it's not available yet, that will stall the second instruction. And finally, if the outcome of a conditional branch is unknown, then we have to wait to figure out what that is before the next instruction can be fetched. Modern processors will typically guess what the outcome of a conditional branch is. We'll talk about that on the next slide. But those guesses might be wrong, and in that case, the incorrect guess will cause a pipeline stall. If we add extra hardware and we compile carefully, we can minimize the stalls. For example, having separate functional units for floating point and integer pipelines allows integer computation to proceed in parallel with floating point computation, which is particularly useful because floating point operations often take longer than integer operations. Let's talk about some modern processor innovations that can help with these, make processors compute more data, more instructions per second. So superscalar processors can have multiple pipelines, and so they can start more than one instruction per cycle. Processors can use register renaming to avoid spurious conflicts between instructions that are executing simultaneously. We'll see an example of that in a couple of slides. Instructions can be executed out of order to make the best use of processor resources. So if we aren't ready to execute one instruction, maybe we can execute another instruction instead out of order, and we use the resources that are available while we're waiting for the first instruction to be able to be executed. Instructions can even be executed speculatively. For example, if we guess which direction a branch will take, we'll start executing the instructions down that branch. If our guess was wrong, we might find out later, and then we have to undo the effects of those instructions. But if we guess right most of the time, which is very feasible for most branches in most programs, then it'll be a win to execute speculatively. Finally, all of these operations, all these optimizations can be somewhat complicated. And so one of the value of these simpler RISC architectures, reduced instruction set computing architectures, is because the base processor execution is more simple, then we can more feasibly implement these implementation strategies that make the processors fast. Modern processors often include multiple cores, which allow different threads of execution to be executed on those different cores simultaneously. We also see today graphical processing units, which are computation units specialized for highly parallel processing of graphics code. That's how you get really realistic graphics to be computed very quickly and shown on the screen. These days, machine learning uses a lot of computation time, and there are specialized tensor processing units, which have some similarities to graphical processing units to speed that up as well. Modern architectures might also include hardware accelerators for common operations such as image processing, media transcoding, encryption, and compression. Let's check our understanding.